Let's have a look at how we implement automation and on why we are implementing automation. What are the primary goals? The goals are these. We would like to actually integrate different types of manufacturing operations to improve the quality, uniformity, minimize the cycle times, and obviously you would like to decrease the labor costs. And we would like to improve the productivity so that in the same amount of time you will produce more products. With automation, we would like to increase the quality of the products, reduce the human involvement, have less engineering efforts, have less labor efforts. We are trying to reduce damages on the work pieces. We are trying to increase the level of safety for labor, and we also would like to decrease the space we are using on the factory plant. So these are the main aims of automation, and we can actually choose the best type of manufacturing operation, manufacturing system, depending on the requirements of your company. Let's have a look at this table. We have three columns: the type of production here, the number of parts produced, and what kind of products we can have with this approaches. For instance, if you send experiment or prototype type of production, then that means the numbers are not high. It's usually around 1 to 10. If that's the case, maybe you can use job shop systems or rapid prototyping facilities. Even you may use ANSI standalone manufacturing systems. And with the help of them, you can produce any type of product. So all products can be manufactured with such kind of for such kind of production quantities. If the number is a bit higher, in between 10 to 5,000, then that means you should be working with some small batches of these products. They might be some missiles, some specific machinery, some dies, jewelry, some orthopedic implants. But if the number is quite higher, up to 100,000, then that means it's a high volume production or batch production. Or in that case, you can produce, as you see, such kind of engines, computer components, some trucks. They're all possible. Then we have the last option. If the number of products is higher than 100,000, then it's called as mass production. And what do we produce with mass production? We produce some, as you see, some food beverage containers, some fasteners, some automobiles. So they can all be manufactured with mass production approaches. We discussed actually job shop systems. It's a summary. And the second one is rapid prototyping facilities. It's sometimes called as digital manufacturing, since on the same machine, you can produce any kind of products. You don't need to generate codes, write G codes for according to the shape of the product. They are all digitized. So it is mostly an automated manufacturing process. And in this figure, we will discuss the basic differences between job shop systems, job shop manufacturing systems, and mass production systems. So for mass production, we can use, if you remember, transfer lines or flow lines. They are all for mass production type of approaches. And in between, we have batch production. So if we go back, you see batches in between 5,000 to 100,000, but mass production is more than 100,000. And job shop is for just up to 10, maybe in maximum up to 50. So let's consider the type of equipment. In job shop equipment, in job shop manufacturing systems, we have general purpose machinery. Here's an example. As you see, we have milling machines, we have turning machines, drilling machines, and as you see, they are randomly placed. We don't have a specific order in between the machines. And in the mass production, we have special equipment, and these equipment cannot be used for different purposes. This is the main difference with respect to other manufacturing operations. And for the batch production, we have something in between. So I'm not going to discuss these properties for batch production. It's always in between job shop and mass production. So production rate is obvious. With mass production, as the name implies, we can produce masses in shorter times, but the production rate of job shop manufacturing systems is very low. We can produce small numbers in a day. And production quantity is obviously related to the production rate. Production quantity is giving you the number of products you are producing, and production rate is the number of products you are producing per unit time. So they are highly related, and we have the same reasoning for this, for these two. Then for the plant layouts, we have obvious differences. In the mass production, we know that we have a line, so the product is moving from one point to the another on a kind of a conveyor belt. So we can say that the plant is actually designed according to a flow line. But in the job shop systems, the plant is mostly designed according to the process. For instance, we put, the milling machines all together, drilling machines together, grinding machines, lathes. So we design the plant actually according to the processes. So this is the main difference between job shop and mass production. Then let's have a look at labor skill. In job shop systems, I mentioned a moment ago that we need to have high skilled labor to use all these various machineries. Since the same person should know the details of the lathe, and also they should know the details of milling machines. And they need to prepare machine codes for various machinery. So they need to have high skills. But considering mass production, it's not the case. With less labor, less skill, you can produce huge numbers of products. Since manufacturing is mostly performed with the help of machineries, with the help of some robots in the environment. Let's have a look at the last property, is part variety. And we know that in the previous figure, we discussed that job shop systems and rapid prototyping facilities have high flexibility, which means that you have high number of part variety. You have flexibility in terms of part variety. For instance, you can produce a mouse and you can produce a kind of a trackpad maybe in the same job shop or rapid prototyping facility, but it's not possible in mass production. You can only produce the same product. Maybe just you can do little modifications on the product, but you cannot switch from, let's say, trackpad to mouse. It's not possible in mass production systems. So this is a summary of what we discussed: piece part production, small batch production, and mass production. Make sure that you go through it, but it's the similar things we discussed in a moment ago. Now let's briefly focus on hard automation and soft automation. What are the differences? We also name hard automation sometimes as fixed position automation. And in that one, your system, your manufacturing system is automated in a hardly manner, which means that you're producing again a single part, but in order to produce a different part, you need to remove some hardware, replace with new ones, and then change the resulting output. So this is a bit actually time consuming, but in the earlier days, since we didn't have much computers around, people were using hard automations or automation approaches for most of the times. And they use, for instance, such transfer mechanisms like straight rails or circular ones. For instance, we have such power hats here. They are performing different manufacturing operations, and we have a rotary indexing table. Once it rotates, then we can perform different operations on the same product. So this is an hard automated system. If you want to change it, then you need to replace this rotor indexing table with the new one. You need to replace the tool. So that's why we call it as an hard automation. By the way, this is a nice example of a transfer line. As you see, the part is moving from station 1 to station 15 in such a manner. We don't have any, let's say, complicated routes, as in the case of job shop production. Here you see we have such transfers between various machines. We don't have an order, but in the transfer lines, we have a nice order between the stations. That's why its productivity is high, but the flexibility is low. Let's go back to our automation topic. We discussed hard automation and said that it was mostly used in the earlier days, but now we prefer to use soft automation. With a soft automation, we can easily modify our automated system by installing new software into our machines, into our, let's say, robots. And with the help of this new installation, we can produce new parts, or we can increase or decrease the speed of our production. They are highly flexible, and that's why people are mostly preferring to use soft automation in their plants. Let's continue with numerical control. It's actually the controlling the movements of machines by inserting some coded instructions into the machine. So once you have written these codes, then you store it into a kind of a disk, or these days we don't use such disks. We use USB, we use Wi-Fi connection sometimes. But the thing is that we need to transfer these commands to the machine. And then what machine does is that it reads all these data, converts them to some signals, and then try to control all the subcomponents of the machine. For instance, if it's a milling machine, it may turn on cooling, it may move its axis. So the machine actually controls the manufacturing process according to the coded instructions. And this is called as numerical control. And here you see absolute, increment, and mixed type of referencing. You will be learning these fundamentals in your machine shop practices or CNC programming lectures. Let me discuss computer numerical control. So in the earlier days, we didn't have much powerful computers, and we didn't have much, let's say, computational power. We didn't have higher memories. We have less memory capacities and less computation power. So what they were doing is that they had an direct numerical control approach. They have a single computer at the center. It's a kind of a server, and then it connects to different machines in the environment. So we have such a connection to different NC machines in the environment. So all of these are actually can be considered as NC machines. So you have, let's say, 4 NC machines in your factory, and then you have a single DNC, direct numerical control system, and then it transfers all these instructions to the machines. The machines actually don't have any computers on themselves, so they only read the instructions and then perform these tasks. But in the distributed numerical control, this time it's in between DNC and CNC type of systems. This time we have a microcomputer on the machines, but we don't have much memory. So again, our DNC server is transferring the commands, but this time we have a bit more computational power on the machine, so it can perform more complicated operations, not just reading and opening and, let's say, cooling. it may perform some other interpolation, for instance, in such distributed numerical control approaches. But with the computer numerical control, these days we have computers on all the machines, so we don't need to use a DNC, distributed numerical control. You can simply install your instructions, even write your instructions beside your CNC system, and then it will perform the manufacturing operations for you. It has a memory, you can store various programs inside, and we have sometimes CNC systems which can easily connect to cloud. So if you have cloud storage, your machine can grab the instructions from the cloud and then perform the manufacturing operations. And in these machines, actually, we need to control all these axes, all these motions. So how we can control them? We have some classification. We have open loop systems and closed loop systems. In the open loop control systems, what we do, we provide inputs. We, for instance, say that x-axis should go to 10 millimeters, but we don't check whether this one goes or not. We simply say that it should move to 10 millimeters. But in the closed loop control systems, we have sensors, and we check whether our axis is at the right position or not. So this is much useful. With the help of sensors, we make sure that our axis is at 10 millimeters, and we do it with the help of sensors, different type of sensors utilized. And if there is an error between the desired position and the actual position, then the controller will perform some computation, and at the end of maybe second iteration or third iteration, our axis will be at the exact position. And this is sometimes called as feedback control. For the position measurement, we make use of indirect measuring systems. We have rotary encoders, actually, which are installed on the shaft of our motion system. By determining the number of revolutions they have, we can easily calculate the position of our axis in our the position of our table on the specified axis. Now let me briefly talk about types of control, or I can focus more on open loop control systems and closed loop control systems. Since we have images here, yes, this is the open loop control system. As you see, obviously, we don't have any feedback like in the case of the below one. The below one is called as feedback control or closed loop control system. In the open loop control system, we simply provide the input and then don't check the result of this operation. For instance, as I mentioned, we may say that the work table should be at 10 millimeters. We provide this information to our driver, motor driver, but we don't check whether this work table is exactly at 10 millimeters. But if you compare closed control system or feedback controller, we have a sensor installed on the shaft of our on the lead screw, and this is an encoder, rotary encoder, and we actually measure the rotation, the angle of our lead screw, and then this information is fed back to our comparator. This is a kind of a computer. We check whether our work table is at the desired position or not. If we have an error in between, for instance, the input, as we said, that is 10 millimeter, but actual position might be 9.8 millimeter, then that means we have an error of 0.2 millimeter. If that's the case, then that 0.2 value will be converted into an analog voltage. This is digital to analog converter, and with the help of this analog voltage, our motor will move a little bit, and the error of our work table will be eliminated. So that's why this is much powerful. But the thing is that obviously it's expensive compared to the open loop control systems. we need to make use of a sensor, a kind of a comparator. So advantage is high accuracy, but the disadvantage is the cost. And in terms of measuring, we have various options. And here you see we have a direct measurement. This is our sensor, and then B and C are examples of indirect measurements. Why they are indirect? Since this is our shaft, again, encoder is connected to the shaft wall screw. Again, this is our rack and pinion system, and our sensor is this one, the rotary encoder. We are measuring the signals. We are trying to calculate the position with the help of these encoders. But if you look at the first one, this is called a direct measurement, since we are directly measuring the position of the table. In the below ones, we are not measuring the position of the work table. We are measuring the number of revolutions this screw made and the angle of it. So which means that after you have this information, you need to do some computation. And you cannot also eliminate the error in between, the mechanical errors in between this measurement and the table. But if you are directly measuring the position of the table, then the mechanical errors in between is not important, since you are directly measuring the last, let's say, thing in our control system. So in the direct measurement, I can say that this is the point actually we are measuring. But in the indirect one, this is the position. We are measuring the angle of our lead screw. But if you do it, then you cannot eliminate the errors you have in this mechanical components, and this will decrease the overall accuracy of your motion control system. Now let me discuss another classification. This is called point-to-point systems and contour controlling systems. In the point-to-point control, what we do, the intermediate movements are not important. For instance, in this drilling operation, yes, I think it's a drilling operation, the important part is to drill these 4 holes, but the intermediate motion is not important. So we can do this process in point-to-point. But if you consider this workpiece, it's the outer profile. We have a complicated outer profile. So we cannot directly say that the cutter should move from this point to the point underneath. It's not possible, since the contour, the region in between this starting and the end points are important. So that's why we should have a contouring system. Otherwise, we will have a kind of a triangle here, and it's not the thing we want to have in the workpiece. So we need to perform a contouring operation. And in numerical control systems, we need to do interpolation. Actually, this interpolation is performed with the computational power on the machine. We have linear interpolation, circular, and parabolic interpolation. So what we do in this interpolation things, we provide some points, obviously, and then tell the machine that you need to perform a linear interpolation in between these points. So it's the simplest one. The machine will simply draw a line in between. But if it's a circular interpolation, then what we do, we need to provide more information. For instance, this is a starting point, ending point, then we need to provide the center, and also we need to provide the angle our actually machine should cover. And for the parabolic one, it's more complicated. You need to give more information to the machine so that it can perform such complicated paths. Here are some examples. For instance, this is a point-to-point operation. It's performing drilling and boring operations. We will discuss all these details in the upcoming chapters. This is again point-to-point, but this time it's somehow a contouring system, since it's also machining while it's moving from this point to the other point. And then we have a bit more complicated case, two-axis contouring system. This time, obviously, it's not point-to-point. It's totally a contouring system, but it's two-axis. It's performing such a motion between these points. And then we have the more complicated one, three-axis contouring system. So we have some conformal surfaces. These are all for the type of control systems. And in order to perform such complicated operations on the parts, we need to write proper codes, proper instructions for the machine. And for that purpose, we make use of special programming languages. You'll see in your CNC programming lectures that they're not complicated. We have some specific commands. Once you follow them, you can write proper G codes, proper sometimes step and C codes, and the machines will accept these codes and perform the manufacturing operations. And the last topic in terms of control is adaptive control. In adaptive control, we have some intelligence in our control system. In the closed control systems, yes, we have some sensors, but we were only doing some subtraction operation between the desired point and the actual point. But this time, in adaptive control, our comparator, not actually comparator, but the computer will check various inputs, various sensors, and then decide according to the current situation. So in this one, we have more intelligence. And why do we prefer to use adaptive control? Since we need to be sometimes we want to improve our production rates further, we want to increase our product qualities, decrease production costs. They will not be possible with the selected machines, selected, let's say, or written codes. You may need to do some extra analysis, have more sensors, and try to embed some intelligence into your machines. It's a nice figure, actually, summarizing an example adaptive control system. So this is the part of the machine here. And this is our written G code. And we have the computer here. The computer actually reads this data and then interprets this data and transfer the commands to the various components of the machine, like drives, tools, spindle motors. And on the machine, we have some sensors. For instance, we have a sensor for the position, for velocity. They're all fed to the CNC controller. But since it's an adaptive control system, we need to have more sensors in the environment, more sensors on the machine. What are they? For instance, we check the load on the spindle, we check the spindle speed, we check the torque, we check the vibration on the machine, and they're all fed to the adaptive control system. And then we have a kind of a powerful computer here. It gathers all these data and interprets them, and depending on the results, it warns the CNC controller, the main controller. And then depending on the inputs coming from the adaptive controller, our main CNC controller again transfers specific commands to the subcomponents of the machine. So with the help of this overall approach, we can optimize production rate, quality, and minimize production costs. Here's another example for an adaptive control. So if you do not apply an adaptive control, this is actually what does it look like. So we have the cutter travel here, and it's the feet per tooth, which means that it's the speed of your cutting tool as this tool is moving from left to right. So let's have a look at the first case, for instance. Variable depth of cuts. If you have variable depth of cut, for instance, and if you make use of this cutter, what will happen? If you go at the same speed, once you come to these regions, especially thicker regions, your actually cutting tool will have difficulties in removing material. But if you decrease the speed, then it will be much easier for your tool to remove the same amount of material. So if it's an adaptive control, then you should change the speed of your tool, cutting tool, according to the thickness of this part. Again, another example, a similar one. This time we have a variable width of cut. Again, as this tool is moving, we need to decrease the speed of the cutting tool. Otherwise, we will harm the cutting tool and we may even break the tool. So this is, again, the same thing we need to do in adaptive control. As our cutting tool is moving to the right, we need to decrease the speed of it. But in the conventional approaches, we don't care about these information related with the product. We don't care the depth of cut or the width of the cut. We always go at the same speed. So you see, if you apply conventional approach, then it will take much more time to remove the same amount of material. But if you apply adaptive control, then that means about for most of the motion, our speed will be much higher compared to the conventional approach, which means that in a shorter time, we will do the same machining process. So this is a nice advantage of adaptive control. So we can say that with the help of it, we can easily increase production rate and product quality. Also, since you are decreasing the production time, we will be decreasing the production costs. Another example, a very simple one, we have a lathe machine here. This is our, the blue one is our workpiece, and we have a sensor here. And with the help of this sensor, we are measuring the diameter of this workpiece. And depending on the error we have between the desired diameter and the actual diameter, our cutting tool moves to the left or right, and the resulting output will have better dimensions.